Okay, hi everyone. Thanks for coming to the Graphs and Matroids seminar. Today we have Chun-Hung Liu from Texas A&M University, who's going to be talking about homomorphism counts in robustly sparse graphs. Go ahead, Chun-Hung.
Okay, so thanks, Shara, for the invitation and the introduction. So this talk is about the counting number of homomorphisms in robustly sparse graphs. But let me start with counting a number of edges. So this is the classical problem in extremal graph theory. So like the classical two-round problem says that if G has n vertices and has no KT subgraph, then the number of edges is at the most a certain number. Or equivalently, it tells us what's the maximum number of edges of an n-vertex graph with no KT subgraph can have. And that's a generalization. It's proved by Erdős Stone. They prove that the maximum number of edges in an n-vertex graph with no h subgraph is a certain number, where h is a fixed graph. And because the number of edges in a graph is the same as the number of K2 subgraphs, so we can consider a more general question. So now we just fix the graph H and fix the graph class G. What is the maximum number of H subgraphs in an n-vertex graph in G can have? And we will call this maximum the extremal function. And we will write this number as Ex of HGN. So in this talk, our graph class only contains graphs that are very sparse, in the sense that the number of edges is at the most linear in the number of vertices. So the behavior is very different from the one in the two-round theorem and the Erdős-Stone theorem, because in their case, the number of edges can be quadratic in the number of vertices. So they are very dense. So we work on the sparse graph class. So we need to handle the upper bound and lower bound for the extremal function differently. So now let me talk about the lower bound. There's a very simple lower bound, but it requires some definitions to say it. So first, let me define the separation of a graph. So it is an ordered pair of vertices called AB, such that A union B contains all the vertices of H, and there's no H between A minus B and B minus A. And we will say the order of the separation is the size of the intersection of the two parts in the separation. Now we say a collection of separations is independent if the following two conditions hold. So one condition is that for every separation in the collection, we need A minus B is non-zero. So A is the first part, B is the second part. But here we don't require that B minus A is non-empty. And another condition we need is that for any two separations, AB and CD in the collection, we want A is containing D and C is containing B. So this definition might look weird, but it can be equivalent stated in another way. So let's see the picture. So suppose the members in the collection are separations AI, BI. And then we can partition the vertices of H into many parts, where one part called the central part is an intersection of all the BIs. So that's the red part in the picture. And each of the other parts is called the peripheral part. Each of them is of the form that AI minus BI. So the central part will be non-empty. The central part could be empty, but every peripheral part should be non-empty based on our assumption. And also, it can be shown that there's no edges between two different peripheral parts. So whenever we have an independent collection, we get such a partition. And conversely, if we have such a partition, then we can obtain the independent collection. So they are equivalent. And also we can show that because there's no edges between two peripheral parts, and each peripheral part is non-empty, so the size of the independent collection is at the most the independence number of H. Okay, so we have independent collection. Now we want to duplicate the independent collection. So what I mean duplicated means I create a new graph. So I will write a graph H, which TC to denote a graph that is obtained from H by duplicating the independent collection C t times. And it's easier to see the picture. So we have an independent collection indicated in the top picture. Now I want to duplicate the collection t times, meaning I want to duplicate each peripheral part t times. So if I duplicate it 3 times, then I obtain the graph in the below. So the below graph is obtained by duplicating the collection 3 times. So such graphs can contain many copies of H, because whenever we pick the central part and the 1 copy of each peripheral part, then we get a copy of H. So actually, if we do the computation, it can be easily shown that if G is the graph obtained by duplicating the collection C t times, then the number of H subgraphs in such a graph G is at least a constant times the number of vertices of G to the size of C. So if we know there exists infinitely many positive integers such that duplicating the collection C t times still create a graph in the graph class, then we get the lower bound for the extremal function. It's big omega of n to the size of C. So we would like to see such independent collection, and we call them G-duplicable, meaning we can find infinitely many positive integers such that duplicated t times create a graph in the graph class. So we know the extremal function is of big omega of n to the k, where k equals the maximum size of a G-duplicable independent collection of separations of H. So that's the lower bound we want to use. It's a pretty simple lower bound. It's easy to prove. And the main result of this talk will show that this simple lower bound actually gives us the right answer for the extremal function up to a constant factor. And in this talk, the graphs we are consider are the graphs that are sparse. And they are not only just sparse, they are robustly sparse in some sense. So here, assume we have graphs that has only linearly many edges. So there are many interesting graphs has this property. So like planar graphs or a graph of bounded maxima degree or bounded degeneracy. Each of them has linearly many edges. But these kind of graphs behave very differently. So for example, planar graphs are very sparse, and they have the robustly sparseness. Because no matter how we contract edges from a planar graph, we still get a planar graph. So the edge density cannot go up by just contracting subgraphs. And the degenerate graphs looks very different. The sparsity is not robust, because if we first take a complete graph KT, where T could be very large, and then subdivide every edge exactly once, then we get a graph that is too degenerate. But we can contract disjoint stars from this two degenerate graph to get the KT. So we can make a two degenerate graph very dense by just contracting disjoint stars. So the sparsity described by degeneracy is not robust. And the graphs with bounded maxima degree is between these two kinds of graphs. We can make the edge density very large by just contracting subgraphs. But if you want to make the edge density very large, then we need to contract very large complete graph. So we need to contract very large subgraph. So in other words, the density is controlled by the radius of the subgraph we contract. So it leads to the notion called the bounded expansion. It describes the robust sparsity that I mentioned before. So here we say a graph class has bounded expansion if there exists a function f such that every graph obtained from a graph in this graph class by contracting subgraphs of radius at the most r has average degree at the most f of r. And we also know the notion called the hereditary. So we say a graph class is hereditary if it's closed under deleting vertices. And the main result of this talk shows that for any hereditary class with bounded expansion, And for every graph H in this graph class, the extremal function is equal to big theta of n to the k, where k equals the maximum size of a G-duplicable independent collection of separations of H. So meaning that the easy lower bound that we mentioned before actually gives the right estimation for the extremal function. And the estimation is up to a constant factor. So this theorem is quite general. It solves many open questions. But before I state that, first let me give you a remark. So here we have an assumption that H should belong to this graph class. But this assumption is pretty mild. It basically just says we are working on a non-trivial case. Because if our graph class is monotone, meaning closed undertaking subgraph, then if H is not in G, then no graph in this graph class can contain H as a subgraph. So the extremal function is 0 in that case. So in this talk, we will always assume H belongs to this graph class. And also, frequently, I would just say the extremal function equals n to the k, instead of saying it's big theta of n to the k for simplicity. Okay, so now let me mention the first application of this theorem. So there's the old theorem X by Epstein, stating that for a proper minor cross family and for any graph H, if the extremal function equals big theta of n to the k for some integer k. So here, the minor means is the graph that can be obtained from the bigger graph by contracting edges and the deleting vertices and the edges. And the graph class is minor closed if it's closed undertaking minor. And this question has many partial results. And probably the most two interesting results are the last two. So one was proved by Wim, Juret, and Wood. They proved that if this minor cross family is the class of all graphs embeddable in a fixed surface, then the exponent for the extremal function is an integer. So actually, I think maybe Tony give the talk about this result last year in this seminar, if I remember correctly. And another interesting result was proved by Hume and Wood. They proved that when H is the tree and the G is one of the following commonly studied minor cross family, then the exponent for the extremal function is also integer. And actually, they can give the description for the exponent. And now we can apply our main theorem to solve this question, because the classical result of mother states that every proper minor cross family has constant expansion. So in particular, they have bounded expansion. So we know the exponent for the extremal function equals the maximum size of a G-duplicable independent collection. And it must be an integer because it's the size of a set. So that's how we can solve Epstein's question generally. And there's a similar question. There was conjecture proposed by Curie, Pavlov, Salia, Tompkins, and Zamora. So it says that assume F is a set of finite graphs. Now consider the class of planar graphs with no subgraphs in H. Then is it true that the exponent of the extremal function is an integer? So this question, this conjecture is incomparable with the previous one of Epstein's question. Because now that this graph class is no longer minor closed, because we can contract H to create a subgraph in F. But this graph class is still a subclass of planar graphs. So no matter how we contract edges, we still get a planar graph. So this graph class still has constant expansion. So again, our theorem can solve this conjecture. And actually, we can prove a common generalization. So we just pick an arbitrary proper minor cross family C and then pick arbitrary hereditary property P. Now consider the graph class consisting of the graphs in C satisfying the property P. Then we know the exponent for the extremal function will be an integer. So these are two applications of our main theorem. So we know the exponent equals the maximum size of a G-duplicable independent collections. But actually, given a independent collection and then testing whether this collection is duplicable or not is not an easy task because we don't know how many times we should duplicate. So it's not a very satisfying description for the exponent, for the extremal function. But possibly this is the best thing we can do because for that theorem, the only information we have for our graph class is have boundary expansion and the hereditary. So we know very tiny thing about our graph class. So in the rest of talk, I will show that if we know more information for our graph class G, then we can get a more precise description for the exponent for the extremal function. And in order to do that, it's convenient to define a notion called the torsor. So a torsor of an independent collection is one of the following two kinds of graphs. So one kind of torsor is called the central torsor. It's obtained by the subgraph induced by the central part of the independent collection by adding edges to make A intersect B a clique for each separation AB in the collection. So for example, the top picture shows an independent collection, and the red part is the central part. And then the red graph in the bottom is the central torsor. And another kind of torsor is called the peripheral torsor. It's obtained by first take a separation in the collection, say XY, and then take the graph induced on the set X, and then adding edges to make XY a clique. So like in the picture, we have three peripheral torsors. So each of them is obtained by the peripheral part together with the vertices in the cut set in the separation and adding edges. Okay, so having this notation, we can give more precise description for some classes that have more precise description. So one such example was about the class of graphs, the class of KST-3 graphs. So in particular, Huynh and Wood has a conjecture about this graph class. So they conjecture that the exponent for the extremal function equals the maximum size of an independent collection of separations of order at the most s-1. So based on our main results, we can see this conjecture is false because they forget to say that the independent collection is duplicate or not. And actually, I know they need to include this duplicability in their statement. They just forgot to say this in their paper because they have proved something different and all of them involved with loss duplicability. They just forgot to say this for this conjecture. So we know that if we include this duplicability, then this conjecture becomes true. But actually for this graph class, we can describe the exponent without using the duplicability. So we can show that the duplicability is equivalent to say every torsor is also KST-3. So we can restate this theorem by just saying the exponent for the extremal function equals the maximum size of an independent collection of separations of order at the most s-1, such that every torsor is also KST-3. And then there are some earlier results. So it's known to be true when H is S-connected, or when S is at the most a 3, or when H is a tree. And then also we can take other proper minor cross family. So for example, we can take the class of KT-3 graphs. And now the exponent looks pretty similar as before. It's the maximum size of an independent collection of order at the most T-2, such that every torsor is also KT-3. And we can also take the class with bounded tree width. So if G is the class of graphs with tree width at the most W, then the exponent equals the maximum size of independent collection of separations of order at the most W, such that every torsor also has tree width at the most W. And the case when H is a tree was known in the past. So we get 3 results that can be stated by using torsors. But there are some cases that we cannot use torsor. So there's something about bounded pathways. So one particular question asked by Huynh and Wood states that what's the extremal function if G is the class of graphs with tree width at, sorry, the path width at the most W, and H is a tree. So they cannot prove anything about this one. And they asked the question about H is a tree because their paper is about tree. And using our results, we can get an answer for this question. So we can show that the exponent for the extremal function equals the maximum size of an independent collection of separations of order at the most W, such that duplicating the collection W plus 1 square times still has path width at the most W. So we still need the duplicability for this corollary. But here we only need to duplicate it a bounding number of times. So checking a separation having this property or not is easy. Okay. So now let me mention other interesting minor clause family. So one of them is stated by using calling deferred parameter. So this parameter is usually written as mu, and it's defined to be the maximal corank of certain matrix associated with G. But the precise definition for this parameter is complicated, so I don't want to state it here. And what's important to us is that if we fix the integer t, now consider the class of graphs with mu at the most t, then this class is minor closed. And moreover, when t is small, there are exact structural characterization for such graphs. So we know that mu is at the most 1, if only if the graph is a linear forest. And the mu is at the most 2, if only if the graph is outer planar. Mu is at the most 3, if only if the graph is planar. And the mu is at the most 4, if only if G is linkless embeddable. So here, linkless embeddable means it can be embedding R3, such that any two disjoint cycles are unlinked in the topological sense. So now let's just consider the class of graphs with mu at the most t. So we know it's a minor closed family, so we can apply our main theorem. And to use this theorem, we can show that the exponent actually equals the maximum size of independent collection of separations of order at the most t minus 1, such that every total also has mu at the most t. So in particular, if we take t equals 4, then we get a case for linkless embeddable graphs. So if G is the class of linkless embeddable graphs, then the exponent is the maximum size of independent collection of order at the most 3, such that every total is also linkless embeddable. And we can go further. We can consider knotless embeddable graphs. So they are the graphs that can be embedding R3, such that every cycle forms a non-trivial knot. So for this one, we can apply our main theorem because the class of knotless embeddable graphs is minor closed. But we don't have pretty good description for the exponent. So we know that we only need to consider separations of order at the most 4. So we know the extremal function equals n to the k, where k equals the maximum size of the G duplicable independent collections of order at the most 4. But we don't know how to remove this duplicability. So we can show that we can use torso to get the upper bound for the extremal function. We can show that the extremal function is big O of n to the k, where k is the maximum size of an independent collection of separations of order at the most 4, whose torso are also knotless embeddable. But we don't know how to prove this upper bound is also lower bound. But if somebody can prove that at the most the fourth sum of any two knotless embeddable graphs is also knotless embeddable, then this upper bound will match the lower bound. So here at the most the fourth sum means clique sum with size at the most 4, meaning we take two knotless embeddable graphs. Each of them has a clique with size at the most 4, and then identify these two cliques into one clique. Then the question is that whether the resulting graph is still knotless embeddable. Okay, so we have talked about a lot about minor clause family. We can also consider topological minor clause families. So here a graph H is a topological minor of another graph G. If some subgraph of H, if some subdivision of H is a subgraph of G. So topological minor cross family also have boundary expansion. So we can also apply our main results to it. So in particular, if we just take KT and consider the class of KT topological minor free graphs, then we get the topological minor cross family. And for this case, the exponent of the extremal function equals the maximum size of an independent collection of separations of order at the most t-1, such that every tensor are also KT topological minor free. And a more interesting topological minor cross family is about crossing number. Probably is the most interesting case. So we fix the surface sigma. Then we define the sigma crossing number of a graph to be the minima t such that G can be drawn in this surface sigma with at the most t crossings. So if sigma is a sphere, then it's the classical crossing number. So the class of sigma t, the class of graphs with sigma t crossing number at the most t forms a forms the topological minor cross family, even though it's not a minor cross family. So we can apply our main theorem. So the exponent for the extremal function equals the maximum size of an independent collection of separations of order at the most 2, such that every its peripheral tensor is planar, and the central tensor can be drawn in sigma, such that there is at the most t crossings. And also the peripheral edges does not contain any crossing. And in particular, if we take t equals 0, then we recover the earlier case when G is the class of graphs embeddable in sigma without crossing. So in that case, we just know the peripheral tensor should be planar and the central tensor is embeddable in sigma. Now there's a variation of this one. It's something called the sigma t planar graphs. So they are the graphs that can be drawn in sigma such that every edge contains at the most t crossings. So if sigma is the sphere, then sigma t planar graphs are also called as t planar graphs, and they are widely studied in graph drawings. Now the class of graphs with the class of sigma t planar graphs is no longer topological minor closed, but it's still known to have boundary expansion. So again, we can apply our main theorem to it, and we get a similar result. But now we just rewrite the embeddability by something related to the definition. So precisely, we need the central tensor can be drawn in the sigma such that every edge contains at the most t crossings, and every peripheral edge cannot contain any crossing. And the peripheral tensor should be drawable in the sphere such that every edge contains at the most t crossings, and the peripheral edges cannot contain any crossing. So it's very similar as the previous one. And there's another example for our main theorem. There's another question asked by Epstein. It's about the extremal function for the graph class. They have a book embedding with t pages. They called it the t-book graphs. So such a graph has a book embedding with t pages, meaning we can first take a union of t half planes, those half planes sharing a boundary line. And then we can embed the graph by drawing the vertices on the boundary line and drawing the edges in the half planes. So this kind of graph is a generalization for orthoplanar graphs, because one book graphs are exactly orthoplanar graphs. And we know the class of graphs with boundary book number has boundary expansion. So again, we can apply our main theorem to it. So we know the exponent equals the maximum size of a G-duplicable independent collection. But for this case, I don't know how to remove the duplicability for this case. So we get the answer for this question. But this question, probably the answer possibly not very satisfying. Okay, so let's about counting the number of subgraphs. And actually everything also works for counting homomorphisms. So here a homomorphism from a graph H to another graph G is a function that maps the vertices of H to vertices of G, such that the mapping preserved adjacency, meaning they have to map adjacent vertices in H to adjacent vertices in G. And we will write the number of homomorphisms from H to G as hom of HG. So counting the number of homomorphisms is an important task. So for example, it is used to define the graph limits. So one way to define a limit of a sequence of graphs, G1, G2, G3, and so on, is to consider the limit of the homomorphism density. So here the homomorphism density is the fraction of the number of homomorphisms from H to Gn divided by the number of functions from H to Gn. So it shows the probability that a random function from H to Gn is a homomorphism. So using homomorphism density to define graph limit leads to beautiful theory, and there are many nice results about it. But it works well only when this limit makes sense. It only works well when the numerator is at the same order as the denominator. And it's not the case when the graphs are sparse. So for example, if you just consider graphs with bounded maxima degree, then it can be easily shown that the number of homomorphisms is linear in the number of vertices. So the proper way to define the homomorphism density for such graphs is to replace the denominator by just using a linear function. So now if we just want to define the homomorphism density for a certain sparse graph class, then we need to determine the number of homomorphisms from H to G up to a constant factor. And that's actually what we have done for counting number of subgraphs. Now we just need to do the same for counting homomorphisms. So more precisely, we want to know the value k such that the maximum number of homomorphisms from H to an n-vertex graph in the graph class G is equal to big theta of n to the k. And the earlier result about subgraphs can be just modified to count the number of homomorphisms. So we can show that for any hereditary class G with bounded expansion, and for every graph H, the maximum number of homomorphisms from H to an n-vertex graph G in the graph class equals big theta of n to the k for some integer k. And then we can describe the integer k by using the duplicability in some sense. Okay, so now we have two results, counting subgraphs and the counting homomorphisms. We want to have a common generalization for these two results. So counting the number of H subgraphs is equivalent to count the number of injective homomorphisms from H up to a constant factor. So actually what we really want to do is to count the number of homomorphisms with a given property. And actually we can do that. So all the results generalize to this case. But now we cannot consider any homomorphisms. We need the property that is satisfied this homomorphism is consistent in some sense. So first, let me just state the formal statement of the theorem. What we can prove is that for any hereditary graph class G with bounded expansion, for every graph H, and for every set of homomorphisms from H to members in the graph class, satisfying certain consistency condition, then we can have the following. The maximum number of homomorphisms in the set S from H to an n-vertex graph in the graph class equals big theta of n to the k, where k is the maximum size of a GS duplicable independent collection of separations of H. So now we have two things to explain. One is the consistency condition. The other is the GS duplicability. So first, let me mention the consistency condition first. So one condition we need is that we want the set of homomorphisms preserve the induced subgraph relation. Meaning, suppose we have a graph G in a graph class, and this graph G has an induced subgraph G prime. Now I want there exists a homomorphism from H to G prime, implies there's a homomorphism in the set from H to G. So I want this relation, these homomorphisms preserve the induced subgraph relation. I also want the set of homomorphisms is consistent with respect to taking isomorphisms. So for example, if I have a graph G, and the G has two isomorphic induced subgraphs, G1 and G2. Now I require there exists a homomorphism in the set from H to G1, if only if there's a homomorphism in the set from H to G2. So we need such a condition. Without such a condition, probably nothing can be proved. And these two kinds of consistency condition will be enough. If you want to count the homomorphism, they don't need to preserve the non-adjacency. So for example, if you want to count the number of subgraphs, we take the set of homomorphisms to be the set of injective homomorphisms. So we don't need those homomorphisms to be preserving the non-adjacency. And similarly, if we want to compute the number of homomorphisms, then the set of homomorphisms we take here, just a set of all homomorphisms. And actually, we can consider common generalization. We can consider homomorphisms that satisfy the extra property that the pre-image of any element in the image has bounded size. So these are kinds of homomorphisms. They don't need to preserve a non-adjacency. But if you want to compute the number of induced subgraphs, now we need to consider injective homomorphisms that also preserve the non-adjacency. So for this kind of homomorphisms, our consistent condition need to include one more thing with respect to that. But this one is hard to describe here. It's also a natural condition, somehow just obtained by modifying the previous two natural consistency condition. But it's just more complicated to say. So I don't want to say it here. So now I need to say another thing in the theorem. It's about the GS duplicability. So this thing just pretty like the G duplicability, like what we mentioned before. But now we need to make S involved in the definition. So before I formally define this, let me just say how I can map an independent collection of H to an independent collection to another graph. So let's see the picture first. Assume I have an independent collection C for a graph H. And I have another graph G and a homomorphism F from H to G. Now this homomorphism naturally maps the independent collection for H to a collection of separations of G. So assume the members in the independent collections are AI, BI. Then we consider separations in G. Each of them is a form f of AI, f of BI. So we get a collection of separations for G. But this collection is not necessarily independent and not necessarily duplicable. But this is a set of separations. So now we can define what I mean the GS duplicability. So now assume S is a set of homomorphisms from H to graph class in G. Now we say independent collection C of the separation of H is GS duplicable if we can find the graph G in the graph class and onto homomorphism F from H to G, such that the set of separations of G obtained by mapping the independent collection C by using F is also independent collection and is G duplicable. So for example, if you want to count the number of subgraphs, we take the set S to be the set of injective homomorphisms. So in that case, we can just take G to be H and then take H to be the identity map, take F to be the identity map. So now the GS duplicability is exactly the G duplicability as we mentioned before. Okay, so that's the terms in our main theorem. So now I want to mention some remark. So our previous theorem is about homomorphisms for graphs, but actually it works for homomorphisms for graphs whose cliques are labeled by finitely many elements. So in particular, it can be used to count the homomorphisms between some objects that are not just graphs. So for example, directed graphs from such an example, because directed graphs can be written as graphs whose edges are labeled according to the direction. And each edge is a K2, it's the clique with size 2. So we can encode a directed graph to a graph whose cliques are labeled. And similarly, we can consider edge-colored graphs. So we just label the cliques by using the color for each edge. And it can also be applied to using hypergraphs, because now we just replace each hyperedge by a clique and label the clique according to the hyperedge. And more generally, it can be worked for relational structures. And there's another remark. So our results is about graph class with bounded expansion. So this is a notion that's studied in sparsity theory. But actually our proof doesn't use anything from sparsity theory. And our proof actually can be used to prove some somewhere dense classes. So in particular, we can consider the class of graphs that are D-degenerate for a fixed integer D. And the one particular conjecture proposed by Hu and Wood states that the exponent function, the exponent for the extremal function equals the maximum size of independent collection of separations ordered the most D. And then we can show that this conjecture is false. And then we give the right answer. So the right exponent for the extremal function is the maximum size of pairwise non-adjacent vertices with degree the most D. So this number is generally smaller than the conjecture bound. Okay, so that's our another result. So now let me briefly mention the proof ideas without giving any details. So the proof consists of 3 steps. So the first step is to show that if the graph G has certain nice ordering, then we can bound the upper bound the number of H subgraphs and the upper bounds of the form like n to the k for some integer k. And simultaneously, we can also find an independent collection of separations with size equal to k. So the next step is just to show that every graph in our graph class has such a nice ordering. So we can get the upper bound and the independent collection. And the third step is to show this independent collection is also duplicable. So it means that the upper bound we showed before also match the lower bound. And it's not easy to say what's a nice ordering here. But for the case that for the D-degenerate graphs, the nice ordering is the one that everybody can imagine. It's the ordering such that if you do the order the vertices V1, V2, V3, and so on, then each Vi only has at the most D neighbors that is of the form Vj, where j is greater than I. So that's the possibly the only interesting ordering for such graphs can have. And this one is good enough for us to prove this. And it's not hard to show that in that case, actually. But for class with bounded expansion, proving these 3 steps becomes harder. And so I don't want to say it here. Okay, so now let me finish the talk by mentioning some open questions. So one open question is about knotless embeddable graphs that we mentioned before. So we don't have good description for the exponent for the extremal function. But if somebody can show that the clique sum preserves the knotless embeddability, then we can get a good description. So let me repeat the formal question again. Assume G1, G2 are 2 knotless embeddable graphs, where each of them has a clique with size 4. Now we define a new graph G that is obtained by the disjoint union of G1, G2 by identifying the 4 vertices in the cliques into a single clique. The question is that, is this resulting graph G knotless embeddable or not? And another question is probably more interesting. So for dense graphs, we have flag algebras or theory of homomorphism inequalities. So they are powerful tool to solve extremal problems for dense graphs. But they don't work for sparse graphs. And one possible reason is that we didn't know how to define the homomorphism density property for sparse graphs. Now we have a way, or a somehow reasonable way, to define the homomorphism density, because we have determined the number of homomorphisms up to a constant. We know how to define the denominator for the homomorphism density. So now the question is that, now can we develop some theory of homomorphism inequalities or flag algebras for classes with bounded expansion, so that we can solve some extremal problems in a systematic way? And the particular question is that, can we do this thing for the class of planar graphs? It's an easier question, and we should consider it first. Actually, this question already asked by Hume, Julian, and Wood when they determined the number of subgraphs for planar graphs. Okay, I should stop here. Thank you.
Thank you so much, Chun-Hung. Let's do a round of applause. If everyone could please unmute, and then I'll count to 3, and then we'll clap. 1, 2, 3.
Thank you.
Oh, didn't come through on that one. That's okay. Thank you so much. Does anyone have any questions? If you do, you can unmute and ask.
I was wondering if there might be a way to like merge what works for dense graphs and sparse graphs. So you got this very it's an amazing theorem, your sparse graph version. The dense is do you think there's like a nice theory that continues on to sort of slightly denser classes and then denser classes?
So I think the first thing is to, so here we have 2 results. One is for bounded expansion and the other is for degenerate graphs. So they are not the same, but they all have linearly many edges. So probably the first thing we should show is that, is it true that as long as we have linearly many edges, then we can do something? So maybe that's the first thing we should try.
Yeah.
Yeah.
That would be nice.
Yeah.
Okay, any other questions? I was wondering about the constant. Maybe that's a mean question, but is it determined by the
constant heating the big theta?
Yeah.
So I mean, it's not small, but for the degenerate case, that's also not too bad. It's something like tower of exponential function, but the height is bounded, like 10 or 5. So I mean, it cannot be the right one, but it's not super horrible. Okay. But for bounded expansion case, that's horrible. The height is a function of h, something like that.
Sounds good. All right, any other questions? All right, thanks again, Chun-Hung. I'll end the recording there and then we can keep chatting. Thanks.
Thank you.